In this lesson, we are going to discuss some more slightly complicated trigonometric integrals and just sort of review the concepts from the previous lesson because there are a lot of things to remember and a lot of identities that you can use. So first we have the integral of sine of x square rooted times cosine cubed x. And recall that the hint is whenever you have an odd power on a sine or cosine, you're probably going to use a Pythagorean identity. And both powers don't have to be odd, only one of them has to be odd. So in this case, if we take off a cosine and save it, we're kind of thinking we're going to let u equal sine. It also would probably be the best to let u equal the thing underneath the square root sign. So let's try to let u equal sine. That means we have to have du as cosine x. So we need to save one of those cosines to be our du, and the others need to be changed into sines. So let's think about this as the integral of root sine x times cosine squared x times cosine of x dx. And this is saved to be du. Now cosine squared can be changed into some combination of sine squareds. Cosine squared is equal to 1 minus sine squared. So this is the integral of root sine x times 1 minus sine squared x times cosine of x dx. And now you're ready to make your substitution. So we have the integral of square root u times 1 minus u squared du. And when that root u distributes, recall that it's u to the 1/2. So u to the 1/2 times 1 is u to the 1/2. When you multiply u to the 1/2 by u squared, you have to add the exponents. So 1/2 plus 2 is 1/2 plus 4 halves, or 5 halves. So u to the 5 halves. So the antiderivatives now are not very hard to compute. The antiderivative of u to the 1/2 is u to the 3 halves, 2/3, minus u to the 5 halves plus 1 is 7 halves, 2/7, plus c. And go ahead and plug back in your substitution. And we have 2/3 sine of x, the quantity to the 3 halves, minus 2/7 sine of x to the 7 halves plus c. So a little tricky with the whole root sine x, but the point is if one of the powers on sine or cosine is odd, that's the thing where you take one off and save it. If they're both odd, you can actually do it either way, and there's more than one correct answer. It's tricky when I assign those problems as quiz problems and realize it after I've done it. Now, when cosines or sines power is even, you have no choice but to use the half-angle identities. So, in this case, you've got to think about cosine to the 4th x as cosine squared x, the quantity squared. And the half-angle identities tell us that cosine squared is equal to 1/2 times 1 plus cosine of 2x. And that whole thing is squared, including the 1/2, which squares to a quarter. So the quarter times the integral. Now 1 plus cosine of 2x, the quantity squared, is 1 plus 2 cosine of 2x plus cosine squared of 2x. And recall that you have to apply that identity again to the cosine squared of 2x. Remember that the angle doubles, so when you use this identity, the angle goes from 2x to 4x. So we have a quarter, integral 1 plus 2 cosine of 2x plus 1/2 times the quantity 1 plus cosine, and the angle doubles to 4x. Close parenthesis, close parenthesis, close parenthesis, dx. A lot of parentheses there. Now distribute the 1/2, combine like terms. 1 plus 1/2 is 3/2. So 1/4 integral 3/2 plus 2 cosine of 2x plus 1/2 cosine of 4x dx. Lovely. And now you're in business. So 1/4, the antiderivative of 3/2 is just 3/2 x. Note about webasine, make sure your variables match. Like if that was 2 theta, make sure that was a theta. The antiderivative of cosine, so we'll have 2 sine 2x, and we're going to need a 1/2 there to compensate. Notice that 1/2 and 2 will cancel. If you see that right away, not a problem, don't write it down. Plus 1/2 times the antiderivative of cosine of 4x is 1/4 sine of 4x, and then plus c. So 1/4 times 3/2 x plus sine of 2x plus 1/8 sine of 4x plus c. So one thing you're going to have to be able to do is distinguish when do you use the Pythagorean identities and when do you use the half-angle ones. And the hint is that if the powers are, if there is an odd power, you can use the Pythagoreans. And I think even in that case, this method using the half-angles won't work, so you can't even try it. If the powers are only even, so this is for only even powers, only even, you use the half-angle identities. And whoa ho ho, a tangent in the root. Sheesh. So we're really hoping we can sub for tangent, and if we can do that, we have to have secant squared to be the du. So let's just go ahead and think, well, u is going to be tangent. My du is going to be secant squared theta d theta, and well, thankfully, that power in the numerator is even, so I can save a secant squared and change the other secant squared into some combination of tangent squared. So that's the same thing as secant squared theta times secant squared theta d theta all over root tangent of theta. And you have to recall that tangent squared theta plus 1 equals secant squared theta. So you're gonna have to know those. So secant squared theta is tangent squared theta plus 1. That quantity times secant squared theta d theta all over root tan theta. And make your substitution now. And this becomes the integral of u squared plus 1 over square root u du. And the way to think about this is that this is like the distributive property just for division. And what you have is u squared over root u plus 1 over root u. And u squared over root u, those exponents subtract, so 2 minus 1/2 is 3/2. So u to the 3/2 plus u to the negative 1/2 du. And so the antiderivative of u to the 3/2 is u to the 5/2, 2/5. That 5 looks a bit like a 3, so let's change that. Well, looks like my eraser disappeared, whatever. So 5/2, and the antiderivative of u to the 1/2 is, u to the negative 1/2 is u to the positive 1/2 times 2 plus c. Let's just insert back what our u's were. So 2/5 tangent of theta to the 5/2 plus 2 root tan theta plus c. All right, now as promised, here is an example to which there is more than one way to do it. So personally, I probably would see the first way first because I know the derivative of tangent is secant squared sort of more readily than the derivative of secant is secant tan. But either way works. If you choose to proceed by letting u equal tan, du is secant squared x, and you have to convert the other secants into tangents. So let's think about this as tan to the fifth x times secant squared x times secant squared x times secant squared x dx. Not the only way, it's just one way. So that's saved to be du. We have the integral of tangent to the fifth x. Now this secant squared is equal to 1 plus tangent squared. And we have two secant squares that aren't the du. So we have 1 plus tangent squared, quantity squared, times secant squared x dx. And now when you make your substitution, you have the integral of u to the fifth times 1 plus u squared, the quantity squared, times du. Now it's pretty easy peasy. Have the integral of u to the fifth times 1 plus 2u squared plus u to the fourth. Distributing that u to the fifth, we have the integral of u to the fifth plus 2u to the seventh plus u to the ninth du. All right, and I'm just going to both integrate and resubstitute. So the antiderivative of u to the fifth is 1/6 u to the sixth. So 1/6 tangent to the sixth. The antiderivative of u to the seventh is 1/8 u to the eighth. And 2/8 reduces to 1/4. So 1/4 tangent to the eighth x. And then u to the ninth will be 1/10 tangent to the 10th x plus c. So that's one way. If you let u equal tangent. This other way is and also works. If you let u equal secant. In that case, your du would be secant x tan x. So you have to save a secant and a tangent. So we write this as tangent to the fourth x, secant to the fifth x, times secant x tan x dx. So this stuff on the end is getting saved. And the tangents have to change into secant so we can substitute. So we have tangent squared x, that quantity squared. And tangent squared is equal to secant squared of x minus 1. So you have the integral of secant squared x minus 1, that's squared, secant to the fifth x. Times secant x tan x dx. So making our substitution, that becomes the integral of u squared minus 1, the quantity squared, times u to the fifth du, which in a pretty similar fashion to the previous example, or previous method for this particular example, u to the fourth minus 2u squared plus 1 times u to the fifth. Oh, the algebra. So we have the integral of u to the ninth minus 2u to the seventh plus u to the fifth du. Now let's anti-differentiate and plug everything back in. In this case, we plug back in secant. So I have 1/10 secant to the 10th minus 2/8 or 1/4 So 2/8 secant to the 8th x, and then plus 1/7 secant to the 7th x plus c. So let's reduce that fraction. 1/10 secant to the 10th x minus 1/4 secant to the 8th x, and then plus 1/7 secant to the 7th x plus c. And what you'll notice is that the answer isn't the exact same as the other one. So they're equivalent. This is the thing with trig, is there's all sorts of different ways to represent stuff. And this one is equivalent to the other one. So it's possible that you might be more than one solution. And if you're uncertain, just make sure that you ask. All right, you have cotangent to the 5th x and sine to the 4th. So to me, cotangent and sine isn't an obvious pairing or combination. So because cotangent and cosecant is sort of the obvious pairing because cotangent's derivative is cosecant squared. So in this case, when you get functions who don't sort of have derivatives of each other that are together in the integral, I would suggest going back to sines and cosines. So cotangent to the 5th x, so cotangent is cosine over sine. This is the same thing as cosine to the 5th x over sine to the 5th x times sine to the 4th x over 1 dx. And notice that a whole bunch of those signs cancel, as in like all of the ones in the numerator, just have the one in the denominator. So you have the integral of cosine 5th x over just a singular sine x dx. Now you can't save that sign to be your du because it's in the denominator, not the numerator. So you have to save a cosine to be your du. So change this into cosine to the 4th x times cosine of x dx. And that's all over sine x. And so your goal here is to let u equal sine, in which case du will be cosine x. So there you go. Now cosine to the 4th is cosine squared squared. So that is 1 minus sine squared, the quantity squared, all over sine x. And now we can make our substitution. So we have the integral of 1 minus u squared, the quantity squared, over u du. And let's do some algebra and expand. We have 1 minus 2u squared plus u to the 4th over u, and divide each term by u, and we get the integral of 1 over u minus 2u plus u to the 3rd. And then anti-differentiate term by term. The antiderivative of 1 over u is ln absolute value u. So ln absolute value of sine. The antiderivative of 2u is just u squared, so minus sine squared x. And the antiderivative of u to the 3rd is 1/4 u to the 4th, so plus 1/4 sine to the 4th x plus c. It's a little bit more tricky than the ones from the previous lesson, but I think still manageable. This next one has not very much space for a reason. It's because it's actually pretty simple if you know your formulas. So the way to think about this one is to break it into 2 over cosine plus sine over cosine. And then realize that 2 over cosine is secant plus sine over cosine is tangent. And you're allowed to just know those formulas. You maybe would encounter tangent on a test, and maybe you could derive it by letting u equal cosine. But for now, it's just the point is that occasionally this might happen. You have to know the antiderivatives of secant and tan. So the antiderivative of secant is 2 ln absolute value secant x plus tan x plus natural log absolute value of secant of x plus c. So the two useful formulas that we had at the end of our last lesson. Now the ones involving cosecant and cotangent are always the trickiest because these are the derivatives that you encounter the least frequently. So they're not as important, but they'll probably show up on a take-home quiz or something just to see if you can handle them. So we could either let u equal cotangent, in which case du is negative cosecant squared x. You have to way to change all the other cosecants into cotangents, which we would. And so that's the way to go. This is it. If you try to let u equal cosecant, you get that du is negative cosecant cotangent, and that means you have to save a singular cosecant and a singular cotangent, leaving the powers odd, and you can't use your Pythagorean identities anymore. So we're saving a cosecant squared. So we're going to have cosecant squared x cotangent to the fourth x, and we're saving that cosecant squared x dx. And cosecant squared x is equal to 1 plus cotangent squared x. Personally, I have to do the derivation of dividing by sine squared in my head every single time. So that becomes, so don't forget that negative sign. I know I wrote it kind of small because I almost forgot it. Negative the integral, 1 plus u squared times u to the fourth, or negative the integral of u to the fourth plus u to the sixth. And then let's anti-differentiate and plug our u back in. So we'll have negative 1/5 cotangent to the fifth minus 1/7 cotangent to the seventh plus c. Now, sometimes tricky. This one is a bit on the tricky side. So cotangent cubed x. So my first thought is, well, I have these identities, and I can use them if I change this into cotangent squared x times cotangent x. When I tried this problem again after not doing it for half a year, I wasn't sure if this was going to work, but it does, so it's always worth a try. So cotangent squared x, that's the same thing as cosecant squared x minus 1. Now, a plain old substitution at this point doesn't work because the derivative of cotangent is cosecant squared, not cosecant squared minus 1. So at this point, let's distribute that cotangent and break it into two integrals. We have the integral of cotangent x times cosecant squared x dx minus the integral of cotangent x dx. Now this first one is so deceptively simple, it's easy to think that it can't possibly be this way. For this first one, you actually let u equal cotangent. And the reason is the derivative of cotangent is negative cosecant squared x. So that first integral just becomes negative integral u du. It's that easy. So negative 1/2 u squared, negative 1/2 cotangent squared x. That's the first part. Now this next part, the way to think about cotangent is kind of like how we would have derived the tangent formula for the integral of tangent. Think about cotangent as cosine over sine. And I've already used let's use w, make a substitution for sine. And the derivative of sine is cosine. Lovely. This becomes minus the integral of 1 over dw. And, well, you can do that. Negative 1/2 cotangent squared x minus ln, absolute value of w, plus c. And our w is sine. So negative 1/2 cotangent squared x minus ln, absolute value of sine x, plus c. Now there might be other methods to integrate this function. This is the one that I came up with, I thought was the easiest. If you think you've fallen short of a solution, you're welcome to let me know and I'm willing to take a look at it. Now the last examples occasionally involve combining certain techniques. So this one, we can't just apply the half-time identity immediately because we have that t there. So this is the thing that I did that maybe was actually had to do that and then do integration by parts. So this is first you do trig and then you do parts. So here's how you start. Start by taking this cosine squared t and making it, using the half angle identity to change it. So we have the integral of t times a half times 1 plus cosine of 2t dt. Let's take that 1/2 out, and we'll have 1/2 times the integral, and also distribute the t. So 1/2 t plus t cosine of 2t. And then let's break it into two integrals. We have 1/2 the antiderivative of t dt plus 1/2 the antiderivative of t cosine 2t. And the foresight that I had was that I can do integration by parts if I have cosine of something. But cosine squared of something is more tricky, so use the half angle to change that cosine squared. And now this first integrand, super easy. The antiderivative of t is 1/2 t squared. So multiplying the 1/2 by the 1/2 you get by antidifferentiating, you're going to get 1/4 t squared. For this next part, so this you're going to need to use integration by parts, so it's a good review. Let u equal t, du is dt, let v equal cosine of 2t dt, and, dv, excuse me, and then v is 1/2 sine of 2t. So this becomes uv, so 1/2 t sine of 2t minus v du, so minus 1/2 integral of sine of 2t dt. There we go. I'm going to distribute that 1/2 through this 1/2. So that gives us 1/4 t squared plus 1/4 t sine of 2t minus 1/4 times, now the antiderivative of sine will be negative cosine, so 2t, and then 1/2 plus c. And so your final answer is to simplify that double negative and multiply the 1/4 and the 1/2. So you have 1/4 t squared plus 1/4 t sine of 2t plus 1/8 cosine of 2t plus c. So that was an example of doing a trigonometric manipulation and then parts. Okay. Now the next one that we're going to do will involve substitution. Actually, this is a double substitution. Substitution plus some kind of trigonometric manipulation. So probably best to let u equal the x squared. It is possible to do this without doing that, but probably it's easiest for most of you to first do that. So u is x squared, du is 2x dx. So half du equals x dx. So that's my first substitution. And this becomes 1/2 integral secant squared of u tangent to the 4th u du. Well, and now you can immediately sub for tangent, but just use a different variable because you already used u. So w is tangent of u, and dw is secant squared of u du. So making that substitution, we get 1/2 times the integral of w to the 4th. So anti-differentiating, we have 1/2 times 1/5 w to the 5th plus c. And first we insert w, which is tangent of u. So 1/10 tangent to the 5th u plus c. And then you insert the u. 1/10 tan to the 5th of x squared plus c. Now our final example looks tricky, but it's actually really simple if you look at it the right way. So 1 plus it would be lovely if we could square root this thing under the root sign, but not unless it was just something to the 2nd power. So, but 1 plus cosine 2x, that looks awfully familiar, doesn't it? It looks like something that involves the half angle. So you're thinking to yourself, well, cosine squared of x is 1/2 times 1 plus cosine of 2x, right? And you don't have half, you have whole, so you could get the 1 plus cosine 2x. You could solve for that by multiplying by 2. So 2 cosine squared x is 1 plus cosine of 2x. Had this been 1 minus cosine 2x, I would have used the sine squared formula. And look, this tells us that we can replace the 1 plus cosine of 2x with 2 cosine squared x because those two things are equal. So this is just a straight up replacement. So 0 to pi quarters square root of 2 cosine squared x dx. And I know it's not pretty, but the square root of 2 is just root 2. So there you go, root 2. Just leave it. 0 to pi quarters. And the square root of cosine squared is just cosine. And 0 to pi quarters, the square root of cosine is actually positive, so you can ignore the whole plus minus business. So, and then the antiderivative of cosine is just sine. So from 0 to pi quarters. And so now we plug in our values. Root 2 times sine of pi quarters minus sine of 0. Now sine of pi quarters is root 2 over 2. Sine of 0 is 0. So we have, well, root 2 times root 2 is 2. 2 over 2 is 1. And just note that if you'd had the integral of the root 1 minus cosine of 2x, then you would have used the fact that sine squared of x is equal to 1/2 1 minus cosine of 2x. So I think, as I've said, a lot of these integrals just involve having lots of experience and seeing lots of tricks, just having lots of tools in your sort of integration toolbox, so to speak. So keep these examples in mind, and good luck.